with your questions. If you have any questions in the topic before the midterm, or if you have, yes, Abdullah.
Yes, Doctor, maybe in the revision, could you go over how we can get the moment coefficient and how we can get it from like the graph? Because I seem to have a problem with it from the graph, even from the graph.
Okay. I don't have a problem with this, but I have the graph going with one of the problems, so we will come and do that. Okay. Anything else? Okay. So the deadline for the homework is today, around midnight, by midnight. Make sure you submit it before that, then I will post the answer. Today, inshallah, we are, I shared my slides already. You see them? Can you see the vision for midterm slides? Not?
Yes, Doctor.
I shared. Okay. So the midterm, inshallah, is going to be very similar in nature and organization to what we had in the quiz. But of course, the content is different. So we are going to have multiple choice problems. We're going to have maybe a short response, maybe a line or two. We're going to have numerical problems. We have 4 chapters, 2 aerodynamics, 3 for the propulsion, 4 for the equations of motion, and 5 for the performance. But you probably have realized that the chapter 4 has no numeric problems because it's the derivation of equation of motion. So numerical problems basically be chapters 2, 3, and 5. So we will try some of these today as we go. When it comes to the multiple choice problem, the first parts of all our exams, you need to be very careful when reading the problem because a single word might change the whole thing. You need to, rather than picking the answer, you need to stop and write the equation on the side because at the end of the day, it is an equation that's translated to words. So you need to make sure you understand, remember the equation, understand the equation, and then pick the answer. So let's try some of this. Equation for power generated by propulsive device is one of these 4 options. And I will leave you for a minute or two to have a look at them. And if you think you have the right answer, just raise a hand. Okay. Let's see how many hands we have. Okay, Muhammad Samir.
الإجابة C.
الإجابة C. Okay, can you tell us why or you remember the equation?
T and velocity, thrust and velocity, the first term is for the power available.
Right.
And the next term after the plus is for the power wasted.
Right.
But shouldn't be minus?
Which one minus?
TV minus half mass flow.
No. Why would that be? TV is the useful power. So you can see it here. It is the useful power. And this is the wasted power. So that would be the total generated power. We are asking for the total generated power. So this is the useful and this is the wasted. Okay. Now it's not the other term because the power is the energy per unit time, and the energy is kinetic energy. So it's m dot, not m. It's per unit time because it's a flowing fluid. It's not the b because we don't have the half of the kinetic energy, and it's not the a because we don't have the difference between the exit velocity and the entry velocity. The wasted energy is represents the difference in kinetic energy between the exiting jet and the entering flow of air. So you cannot have a plus sign. It has to be the negative sign. Okay, so the answer here is C, and it's useful plus the wasted. Okay. Okay. Let's try the next one. Thrust specific fuel. Oh, there is a raised hand also. So, Mohammed Samir, do you have a question or? Oh, okay. So question number 2. Thrust specific fuel consumption. Is it the weight of fuel consumed for unit time, thrust input per unit time given, weight of fuel consumed divided by thrust input? Very confusing. They all seem the same, so you have to identify what are the differences. And in order to do this, you need to memorize the equation or remember the equation because it's a definition of what's thrust specific fuel consumption. So let's see if someone can give a try. Okay, Abdullah Al-Asmari.
Yes, it's C, Doctor.
Also C. And why is that? What's the definition of thrust specific fuel consumption?
I don't know the definition, but I know the equation.
Yeah. Yeah, I mean the equation. What's the equation?
Yeah, it's weight of the fuel consumed by the thrust output, and the only output here is C.
Yes.
Oh no, there's D, but the D has units per mass, which is not correct.
Yeah, unit per mass here is just a confusion time. So when thrust specific fuel consumption is m dot fuel by thrust, what does that mean? What's the mass flow rate of fuel? That means we feed into the engine what amount of fuel per second or per hour or per minute, whatever, to get 1 pound of thrust. So that's the output thrust. So we have to divide by the output thrust. And on the top, it's the weight of the fuel per unit time for any time. So think of it as M or W dot. That's why we have the time increment. And then it's divided by the thrust. That's the specific fuel consumption. Okay. Okay. Let's see the third one. The relationship between the L over D max and square root of zero lift drag coefficient, the square root of the zero lift drag coefficient. Is it directly proportional, equal to, constant, inversely proportional, none of the above? Okay, Mu'taman.
D, Doctor.
G, which G is
Inverse.
proportional. What's the square root of zero lift drag coefficient?
Square root of CD naught.
Square root CD naught. So it's inversely proportional to square root. And why is that? What's the equation relating L over D maximum to the root square of CD naught?
L over D maximum equal to 1 over square root of 4K CD naught.
Oh, that's a very good thing to remember. Okay, now that tells me something about, okay. So here is the root CD naught. Here is the equation, L over D maximum, 1 over root square 4 CD naught K. And you probably realize here, this represents the performance of the aerodynamic performance of the wing. The higher L over D maximum, the more efficient is the wing design. And it's a function only of two factors, CD naught and K. Okay. And both factors exist in the drag polar. So that's why the drag polar is very important. It's the only factor that affects the L over D maximum, which is an important number in the design of aircraft. We will later find that the size of the engine will depend only on this value. It will be simply 1 over this value. The thrust weight ratio, or the thrusts of the engine divided by the weight of the aircraft, roughly is equal to the inverse of this value. So any reduction you have in CD0 means you will increase L over D and you will reduce the size of the engine. The same goes for K, which is the proportionality factor with the induced drag. Okay, so it is inversely proportional. Okay, any questions in this part of problems before we move on to numerical problems? Okay. Let's read this one. Turbofan engine on a test stand in the lab operates continuously at a thrust level of 60,000 pounds. So we are testing the engine which has a thrust of 60,000 pounds on the ground. It's not flying or anything, it's on the ground. It has a thrust specific fuel consumption of 0.5 per hour. That means every hour we have to feed in 0.5 pounds weight of fuel. The fuel reservoir or tank here feeding the engine holds 1,000 gallons of jet fuel. So that's the size of the engine. If the reservoir is full at the beginning of the test, how long can the engine run before the fuel reservoir is empty? That means if the fuel tank is full, how long you will be able to run the engine until it runs dry. Now you see here it's given the fuel in terms of volume, which is not very helpful because we don't have equations involving volume of fuel. They are all weight flow rate or mass flow rate. So that's why this piece of information is crucial to be given, which basically is the density or the weight density of the fuel. A gallon of fuel is 6.7 pounds. So every gallon weighs 6.7 pounds. We have 1,000 gallons. The question is, how long would it take to run dry? What this question tests is your understanding of this thrust specific fuel consumption. You know the equation of TSFC. Okay. So in order to solve it, we have to use the definition of thrust specific fuel consumption. It's m dot fuel divided by the thrust. How much fuel you have to pay per second in order to get 1 pound of thrust. Well, we know the thrust is 60,000. We know the thrust specific fuel consumption is 0.5 per hour. So the only unknown here is the mass flow rate or the weight flow rate. Okay. Now I can determine this by multiplying 60 times 0.5, giving me 30,000 pounds per hour. That means in order for this engine to run for 1 hour, I will need 30,000 pounds of fuel. Okay. However, we are given that the fuel tank is 1,000 gallons and each gallon weighs 6.7 pounds. So that means the total weight of the fuel is 1,000 times 6.7, 6,700. So you have this much fuel. You need this much fuel to burn every hour. So if I divide both, that will give me the duration of the test. 6,700 divided by 30,000 will be 0.23 hours. Less than quarter of an hour, about 13 minutes maybe. And then the fuel tank will run dry. Okay. So nothing here, simple math. The only thing that you need to remember to solve the problem is this. The thrust specific fuel consumption is m dot divided by T. Okay. Any questions? Questions? Yes or no? Okay. Let's see the next problem. The BD-5J aircraft equipped with plain flaps. Now, you have read that name of an aircraft in several problems in chapter 5, the performance chapter. It would be nice to have a look at the aircraft so that you have appreciation of the numbers you are using. And later on, when we start doing design, the shape will give us some suggestion on some assumptions of values that are not there. So this aircraft, the BD, has plain flaps. We are given this problem. This was a very famous, very popular micro aircrafts in the 1970s. Very, very light aircrafts, very small aircraft, single passenger. It came in several versions. One of them was internal combustion engine with a propeller towards the back, and another version with a small jet with an intake here and the engine also in the back. Okay. As you can see, the wing is tapered but unswept. The wing is not swept, and this can be clear from a top view also. Now the problem reads, the airfoil section at the root is a NACA 64212, and interestingly enough, it's a thicker section at the tip, 64218. Hopefully you realize that the 212 means it has a 12% thickness ratio in the root and 18% thickness ratio in the tip. That means this wing is thicker in the tip than in the root, and maybe you realize that a little bit in the figure. Okay. The question is, estimate the stalling speeds of this aircraft at sea level. Calculate VSTOL. What is the slowest speed this aircraft can fly at sea level? And that's stall speed. Okay. Now, last time we talked about the maximum speeds as well as the minimum speed. When we talked about maximum speed, where did we get it from? When I say the maximum, where did we get it from? فهد القحطاني. فهد؟
ايوه يا دكتور.
ايوه. Maximum speed. How did we calculate maximum speed?
من القانون نفس الهومورك
اللي هو
TA max over weight.
Okay, so equating a TA
max
TR and we have تمام. Okay, so that's the max. So it's the intersection with the available thrust. For the lowest speed of the aircraft, we had two things: either the stall speed or the speed at which the thrust is not capable of providing a steady flight. Here he's asking of one of them only, the stall speed. Okay. So in order to calculate the stall speed, what do you need? Hatim. How do you calculate stall speed?
نحتاج الويت.
Yes. What else? What type of equation? How are you going to get it?
هو الايكويجن اللي هو 2W على الاس في سي الماكس في الدنسيتي تحت الروت.
Good. Okay. So we will start by writing our equation. Okay. So the equation that we need, 2W rho S1 over CL max. Now, in analysis problems, just like the ones you are having in the exam or the ones you are having in homeworks, all the way through maybe week 8, you will have all the information of the aircraft. You will not make any assumptions in them. But later on, when we start doing design, starting week 9, you will be you will need to assume some of the values that are not given in problems. In both cases, you will probably find more information than one you need. So, for example, information given for this problem are this. For this aircraft, the wingspan, the wing platform area, the total weight, the fuel capacity. Now, that doesn't mean I have to use all of them in every problem, because that's the nature of design. You will probably have more information than what you need. You have to pick the ones that are relevant. So for this problem, as Hatim mentioned, we need the platform area. So we have it. We need the takeoff weight. We have the takeoff weight. We need the density at sea level, because the aircraft will be stalled at sea level. Density at sea level from the standard atmosphere data 0.0023. Probably have now, by now you remember the number. You don't even need to get it from the textbook. And the only thing that we need still to find in the equation is the CLmax. We don't have that. So if the aircraft, if we have the figure that shows CL versus alpha of that airfoil, I will go and get it. Okay, especially if the figure has a plane flap as well, but we don't have that. It's not there in the textbook. In an exam, you don't have that. In design, maybe I don't have that. But if I have the luxury of going into the internet, doing a search, getting the CLmax of this airfoil, I will do that. However, we have an alternative here. The airplane is equipped with a plane flap. And we had a table that tells me what is CLmax for different types of high-lift devices, including plane flaps. So in order to get CLmax for this aircraft, I will go to the plane flap and I will pick the appropriate value of CLmax. Now, we mentioned this last time, but no, not last time, last week, but I need to mention it again. In takeoff, the flaps are not fully deployed, so it's only 20 degrees deflection of the flap. That means the CL that we get is not the maximum, absolute maximum of the aircraft. We get a high one, but it's not the absolutely maximum CL. We get maximum CL when the aircraft is in landing, because the flaps are fully deployed. Okay, so that's why we have to look for the landing value. So for a plane flap, the landing CLmax is somewhere between 1.7 and 2. I can take the average within that range, so I will take 1.85. Okay, now that's only because I'm solving a problem, but in design, maybe I can later on, not for the major, for the midterm exam, but for later design problem, I might want to take 1.9 or 2 if I have well-designed flaps, or 1.7 if I'm not very sure about the design of the flaps. But here, for problem solving purposes, we will take it like the average, 1.85. If you have a different type of flap, I will take the appropriate value. Now, I need to remind you that this is not just CLmax, it's CLmax over cosine the sweep angle. But since this wing is not swept, the sweep angle is 0 and the cosine is 1. But if it was a swept wing, then this 1.85 that I will get from the table have to be reduced by multiplying by cosine the sweep angle, because sweeping reduces the effectiveness of the flaps. Okay, so putting the CLmax here with the wing platform area and the takeoff weight, we will have the stall speed of 109.3 feet per second, which is rather a slow speed or low speeds. If you convert this to meter per second, it would be about 119. That's lower than your car. So this aircraft can fly slower than your car. Okay, and that's a good thing, not a bad thing, because the slower the aircraft can fly, the more safe it is. Okay, that can fly. I'm not saying that it will cruise at this speed, but it can go as low as this speed. That's a good thing. Any questions in this problem?
Doctor, any question like this, how will we be given the givens?
Information? Yes, they will be given in the problem, just like here. So, for example, maybe at the beginning of the exam, I can give you information, all this information of the aircraft, and then on every problem, you will have to pick and choose which data is relevant. So I can give this at the beginning of the exam, and in the performance, in the aerodynamic question, just like the question that we have here, you will use the wing area, and you will use the gross weight, right?
Yes.
Okay. I can provide you with the table, of course. You will need that table for high-lift devices, so that can be there. But in a problem of the propulsion, you will use the fuel capacity for the tank, you get the power of the engine. So I will not give you the specific information in every problem, but I can give it in general at the beginning. And you will pick the appropriate one. Is that clear?
Yes.
Okay. And if there is need for other specific problem on certain tables, in certain problems, I can give this when it comes. So maybe there's something general at the beginning and then specifics on each problem. Other questions? Yes.
Why you choose the landing CL max?
Okay.
Why didn't you choose the takeoff?
Okay. What speed do you want to calculate? The stall speed. Do you agree it is the slowest speed the aircraft can fly? Okay, so you have to consider the condition when the aircraft is at slowest. To get that slowest speed, the flaps have to be fully deployed. Because what is the flap? The flap, basically you are you are bending the cross section, the airfoil, to increase the camber. So in order to increase the camber, we can deflect the flap 10 degrees, 20 degrees, 30 degrees. So the more camber you have, the more deflection you have, the more CL you get, and the slower the aircraft can get to. So if you want the slowest speed, you must have the maximum deflection, and that's the landing. Why is that? Because aircraft land at speeds lower than the takeoff speed. We land almost at the stall speed, almost. And why is that? Because we're not worried that the aircraft can stall, because it's landing. So I wish the aircraft would stall just at the time when it touched the ground. Okay, but in takeoff, the aircraft cannot take off at stall speed, because if something goes wrong, it will fall off from the sky. So takeoff is at speeds like 1.1 or 1.2 VSTOL. Okay, so whenever we are talking at VSTOL, we are considered, and we have high-lift devices, flaps, we will use the landing setting. Is this clear?
Yes,
okay.
Thank you, Doctor.
Okay. Other questions? So moving on to our next problem. Okay. Consider a straight wing of aspect ratio 6 NACA 2412 airfoil. Now this start to get familiar. You probably now you memorize by heart the information of the 2412 airfoil because of the so many examples in the textbook and the problems that you have solved on. Okay, but it's still the airfoil for this problem because this is the one that we have information for. Basically, I mean the CL alpha and CD alpha and CDCL curves. But of course, you can have another one in the exam. Assume span efficiency factor to be 0.95. What's the ratio of lift to drag for this wing when flying at 6 degrees angle of attack? He's asking what's L over D. Now, there is no point in going and calculating L by itself, 1/2 rho V square SCL, and then calculating D and dividing. Because when you do so, you could save yourself some time by realizing that the 1/2 rho V square term will cancel from the lift and from the drag. The S, which is the area, will cancel from the lift and the drag. That means when we ask what's the ratio of lift to drag, that means what's CL over CD, just the coefficients. Okay, what's CL over CD? So the problem now is to calculate CL and CD. Now, whenever you have any requirement that has lift and drag together, think first of the lift and then go to the drag from the drag puller. So let's focus on the lift. So the question now becomes, calculate the lifts of this wing, 6 degrees, aspect ratio 6, NACA 2412, straight wing, not swept. Oh, that sounds very much like homework problems. Actually, it is one solved example of this wing for the CL part. Then from the CL, I can go and calculate the CD. Okay, so what I presented in the next slide with the CL, something that you have seen before, which is how to calculate the CL. I hope you still remember that from the quiz. To calculate CL, you need to calculate the slope, which is A, then multiplied by the angle. So the slope A is equal to the slope of the airfoil divided by 1 E0 by E aspect ratio. And that's because it's not tape, it's not swept wing, and it's a high aspect ratio wing. Aspect ratio 6, and it's not swept. So this is the proper equation to choose. And I can give it to you in a multitude of ways. One of them, just like in the exam, where I ask you to pick the appropriate equation, or sometimes it can be given among formula sheets or maybe with the problem. So that's the slope. When you calculate it, you will need the slope of the airfoil. That's from the airfoil. I'm not going to do this again because we did this in a couple of examples. Reading from the airfoil, it was 0.015 per degree, 6.02 by radian. And when you put the 6.02, this will give you a slope of the wing, not the airfoil, of 4.5. So the airfoil has 6, but it went down to 4.5 because of the aspect ratio. Now I need to multiply it by the 6 degrees, but the airfoil has a 0 lift angle of attack of minus 2.2, so it's A times alpha minus alpha. This one is not alpha, it's A, it's the slope, and this one is the angle of attack. Okay. If the wing airfoil is symmetric, the alpha lift equals 0 is 0, just like the quiz problem. It was symmetric, there was no 0 lift angle of attack. So this one is 0, simply multiply by the 6. So the easy part here is what's the lift coefficient, 0.648. Okay. And that's, I think, example 5.2 or 5.1 in the textbook. Now we need to do the second part. What's the CG? From this lift, what is the value of CG? Okay. So how are we going to do this? Any hands? How to calculate CG?
Doctor, I'm sorry, I have a question.
Yes, question, Hassan.
How can I get the accurate slope? Because if I get different points, sometimes the slope will change.
Yes, two things. Of course, you are worried, and you are right to worry about the autocorrection in the exam, right? There's a final answer and there's a range, and everyone can think of that. Well, pick 2 points that are far apart on the figure. That's rule number 1. Don't get 2 points that are very close when you calculate the slope. So when we calculate the slope in here, you see this 0.105 per degree. How was it calculated? I'm going to jump a little bit for the curve. No, I don't have it here. Unfortunately, I have the drag. So you pick 2 points in order to get the delta y and the degrees or delta x. 2 points far apart. And do you get the other thing to realize that, can you mute? Okay, the other thing to realize that when you get that slope, it will not be more than 2 pi. That will give you like an upper bound on doing mistakes. For 2 airfoils, it will not be more than 2 pi. 2 pi is 6.28. Okay, but it will be close. So we know that it will be around the 6. Okay. So that's it. Of course, in real life, no one does that. We will not read from the curve. We have actually the curve digitized for all airfoils. I will look to any airfoil library on the internet and I will get the CL alpha for that particular airfoil. But in an exam or so on, or a quiz, that's not feasible. Okay, so you'll have to read it from there, unless it's given. Sometimes A naught is given as input to the problem, and then you will have to calculate the A, just like in the quiz that we had. Okay. Okay, so back to my question, how to calculate the drag. I know the CL is 0.648. How are we going to calculate the drag? Any suggestions? Okay, Abdullah.
Maybe you can calculate the induced drag, and then from the graph get add them together and get the total drag.
Yeah, very good. Now, I need you all guys to get the lecture of this section 2. I don't want to just one of you to get it and just answer a question. It would help. That's a plus for your section. That's very good. Get the lecture from there, have a quick look at it, and that would be like a good introduction to the class. It always helps. I really wish I can switch you guys every now and then, because I typically get more response on the second section than the first. So there is nothing wrong with that, nothing harm. Just get prepared. It's just like being prepared. So if you can get it, have a look at it within 10 minutes, and then we will all be on the same page in here. Okay, so yes, in order to get the drag, I need to use the drag polar. So how I'm gonna get to the drag polar? Well, it has two parts. The drag polar has the induced part as well as the parasite part. Let's start with the parasite part. Okay. For the parasite parts, this is where we are going to read the curve. And whoever asked, can we get the CM? Well, just by incidence, the curve, I have it here, but it's not always the case. So next time you want me to address something, just tell me before the class so it's ready. Anyways, so that's the drag polar that we have here, and that's the moment coefficient. We want to read the CD naught. Okay, now I can read it as a function of an angle of attack if I have the CL alpha curve, or as a function of CL, just like in here. We have calculated CL to be 0.648. So at 0.648, I have to read the drag in here. Now, but I have several drag polars. Drag polars are the one that looks like dangling chains. This one, okay? That looks like a cosine function. These are the drag polars. I have several ones. Which ones to choose? Well, if you read in here, for each one of these curves, I have different Reynolds number. And for the one that's separate on the top, it has a standard roughness airfoil. It has a rough airfoil. That's why the drag is high and the curve is above all the other curves. So ideally, I will calculate the Reynolds number, and I will pick the appropriate curve for my case before reading CL on the curve, giving me CD. However, since in that range, they are almost all on the top of each other, there is no point in doing this. I would better just read on any of them in here. Okay, so for 0.648, you can read the drag to be 0.0076. Will I have reading differences between different students? Yes. Will I have differences in the final answer? Yes, but it will be within a range. Okay. So in putting the final answer on Blackboard, I typically put a range depending on what we are reading at, plus or minus maybe 20%. Okay, so and then we check after you submit that it was correct. So reading this, the CD naught will be 0.0076. This is the parasite term. This is the skin due to friction, not due to lift, not the induced drag that Abdullah was talking about. This is the one that's due to friction. So that's the first part. Then I need to calculate the part that's induced drag, the one that's due to lift. The induced drag term, and again, I don't have to provide this equation, assume you know this one, because that's the equation of the drag polar, CL square over pi E aspect ratio, where E here is the span efficiency factor. How efficient is the span? The longer the span, the higher is the efficiency factor. And efficiency factor is given in the problem to be 0.95 in the problem. So we have everything in here. Calculating induced drag turns out to be 0.0234, much higher than the parasite drag. You see this 0.023, and the parasite drag was 0.0076. Okay, so that's like more than 3 times at least of the parasite drag. And that's because the wing aspect ratio is not very high. So now we can add both types of drag because that's the total drag. I don't want to lose the question. The question was what's CL over CD? So I need to find the total CD, which is the sum of parasite and induced. Add them. Turns out to be 0.0312. And since the lift is 0.648, dividing it by 0.0312 gives me a ratio of about 21. So for this wing, the lift is 21 times the drag, which is a good ratio, high ratio. Typically, it would be above 15. Below 15, it would be a very low ratio. So 21 is a good ratio. This ratio can be increased if the aspect ratio increase, of course, because it will decrease the induced drag. This ratio can be increased if I have a high lift devices because it will increase the CL, the 0.648 that we have here. Okay, so all these are factors that can increase lift to drag ratio. Any questions?
Doctor?
Yes.
So the total drag is equal to the drag polar plus the induced drag?
No, not the drag polar. The parasite drag plus the induced drag. Both of them together is the drag polar. You see, this is parasite and this is induced. Let me show you the equation of the drag polar. I think we had it somewhere in the brief. Here it is. Parasite plus induced. The term that's independent of the CL is the parasite drag, and the term that's induced is the that depends on the CL. Now, why did we read it from here? Remember, what we read from here is for the airfoil only. This curve is not the drag polar of the whole aircraft or the whole wing, it's the drag polar of the airfoil only, because it has nothing to do with the span. No matter what the span is or the aspect ratio, this curve is the same. It's only for the airfoil. So think of this as the 2D drag, the drag due to the two-dimensional airfoil. And the other term that we calculate here, what is that? That one is the effect of the 3D, the effect of the aspect ratio. And then when we add together, that will give me the total drag of the wing. Okay, 2G coming from the airfoil drag polar and the GI due to lift. Is this clear?
Yes, doctor, thank you.
Okay. Now, there was a question reading of the moment coefficient. I understand that it's very difficult to read from a figure like this. So if we ever have a moment, I have to enlarge this a little bit. The point in reading the moment coefficient, I can come at the CL, at which angle 6 degrees will have a certain CL, so it's like 0.648, and I will have to read the moment coefficients from here. It's negative. All of them are negative with maybe, where is that? No, not even here. All of them are negative, as they should be, by the way. Okay. So yes, it will be almost constant at minus 0.05 or 0.048 in here, except maybe at a very high lift coefficient, where it's going to be very high. But that's not the case. This is only the case because that's the only chart that we have in the textbook. In reality, go into the net and do a search on airfoil library. There are so many online airfoil libraries, and you will have way better figures than this with more accuracy, Where you can get the slope already there, it's there. You don't have to calculate it. And that's the way that we're going to do it later. We will not stay for all our life solving problems. We will use the resources that we have. So right after the midterm, when we start doing design in chapter 6 and 7, no, not after midterm, maybe by week 9, I would say. You can use any resource. You don't have to stick to the textbook. Log into the library, click the name of the airfoil. You will get all the figures colored. Get what you will not calculate the slope. It's going to be there. You can even find Java applets on the net where you can put the aspect ratio by itself and taper ratio, sweep angle. It will draw the wing and it will give you the drag, one lift and lift drag ratio, and you can use that. You will not be only solving the problem, except when you have to in a quiz or like in the project, for example. You don't have to use this equation. Go ahead and do it. Get it from the net. Okay, get it from a software. Do a fluent run. Depending on what are your capabilities, what resources do we have. Okay, so we will do this inshallah after the midterm. So I'd like to stop here, and if you have any more questions, you can ask me either by WhatsApp or email over the weekend once you start study. But please make it on the group so that the questions would be beneficial for us all. Maybe some of your colleagues would have the same question you want to ask. So when they read the question answer, that will help them too. Okay, that would be more beneficial for all. And feel free to ask any question. There is no simple question and tough question. There is no silly question. The only silly question is the ones that are not being asked. Okay, so anytime. The other thing, we need to prepare for the major exam for the midterm. Now it's called midterm. The video cams have to be on all the time. Make sure you have your calculator ready. Make sure you upload the file to the system because I will not accept them on emails. So give yourself some time to upload on the system. Make sure you write the final answer. I had some of you who did not write the final answer. They did it on paper, but they didn't write it on Blackboard. So please write the final answer. I also wrote comments for you. I don't want you to get the grades like this for the quiz. I put some comments on the attempt. I need you to read. I was talking to your colleagues in the previous section. They told me it's not there. I think I did like an between the two sections. I did an update and they can see it now. So just wait for an hour or so and you will see your comments. Click on the comment and you will see a feedback to learner, and that's comment for every one of you. Would be, for example, you did that wrong in question number 3 or you did that on question number 4. Not only the final answer, but the steps of you. So within an hour you should see it, inshallah, on your system as well. And that's for you, Ali Khalifa, if you're here, because he drew my attention that you cannot see it. So that's why I'm updating. Okay, Shwab. So I will see you, inshallah, on Sunday, 8 o'clock. That last word. I just talked to your colleagues and said 6:30 because no one had a conflict, but I received an email between the two sections that some of you still have the conflict. So it will be 8 o'clock. I hope you don't have a conflict with that. Okay, so I'm gonna update the announcement now. Yes, Hassan, good.
Doctor, can you send us the formula sheet?
I can send the formula sheet, yes. Tomorrow you will have it. But that doesn't mean it's the information sheet, it's the formula sheet. Because for informations, there can be additional informations in each problem. But yes, I will send the formula sheet. Okay? Okay, Shabab. So I'll see you, inshallah, on Sunday, 8 o'clock p.m. Okay? Shukran.